we had force equals MA, which equaled to mg minus k times my s plus x. And when that got distributed, this was our equilibrium, which added to 0. So this turns out to be minus kx. So we have MA equals minus kx is just up kx. Now we're going to look at damped. Damped is a multiple of velocity. And just for an example, it could be air resistant. And again, air resistance would slow it down. So what we have here, if we play off of our last one, this is our mass. Our undamped basically had a force of kx only, okay? So now we are going to have something just like the spring constant working against it. We're going to have your damping, it's a multiple of velocity, working against it. So when we write this out, force equals ma, your sum of your forces, basically, which is equal to, looking at our picture, it's going to be minus kx minus bv. Remember, going up, pulling up is negative. The original up here, g, your gravity goes down, it pulls it down, and what's pulling against it are the things going up, which pulling against gravity. So writing this out, we have ma, this is our equation here, plus bv plus kx is equal to 0. Our a is our acceleration, so our m d squared x in terms of time, plus beta v plus k. Oh, and v, by the way, is our velocity. A is acceleration. V is our velocity, which is our dx dt, plus kx equals 0. And just to keep this list going, m is our mass, my beta is my damping coefficient, and k is our spring constant. So we basically have our equation right here for damped. Now, usually you just need to find m, beta, and k and plug it in. You can solve it like normal. They're constant. They're going to be constants, so you can use constant coefficients to solve this. There will be 3 cases since we are using our constant coefficients. And basically, just some new terminology here. It can be overdamped, and that's when you solve the system and you basically get 2 distinct solutions, real. 2 is critically damped, is our repeated root. And 3 is our underdamped. Not a big surprise. That was our imaginary case, which we had when we were undamped. So that's our 2 imaginary roots. Okay, let's do an example. Okay, this is kind of a long one. So we have a 4-foot spring, measures 8 feet after mass weighing 8 pounds is attached. The damping force is square 2 times the instantaneous velocity. Find the equation of the motion if mass is initially released from equilibrium with downward velocity of 5 feet per second. Find the time at which, so we find the equation, and then find the time at which the mass attains its extreme displacement. So it sounds like a maximum. From the equilibrium position. What is the position of the mass at that instant? So let's see what we can get from all this information. So if we want to draw it, we have 4 feet spring. So that's the spring is 4 feet. It measures 8 feet after the mass weighing 8 pounds. It measures 8 feet after 8 pounds is attached. So that means this is also 4 feet. The spring is originally 4 feet. So S equals 4 feet. And x equals another 4 feet. So we can use force equals ks to find our K. Our force is going to be the 8 pounds. Our weight is also 8 pounds. So we'll have to convert that to slug. Okay, so our force is 8 pounds. Our K we're looking for, and our S is 4 feet. So if I divide by 4 feet, K equals 2 pounds. So there's my K. So remember our formula. So we have Kx, and now we have beta velocity. Sum of force equals ma equals minus Kx minus beta velocity. So ma plus Kx plus beta velocity v. Switch those. And now switching acceleration and velocity to calculus. Dx dt. And we have our K. And if we read it, the damping force is square root of 2 times the instantaneous velocity. So that sounds like beta is square root of 2. So that's square root of 2 times the velocity, which is x. We have beta, we have K. What about m? So the weight is 8 pounds. The weight equals mg. We need the mass. 32 per second squared. Divide by 32. And that looks like it's a slug. So we have 3 constants we need. Mass is 1/4. Beta. So using x equals e to the RT. B squared is 16 times 2. Which is our middle one, our critically damped. So my fundamental set. Motion. My x of 0. My initial distance. Let's go back and read it. So it's initially released from equilibrium, which means x of 0 is 0. With downward velocity, there it is, 5 feet per second. That's my x prime of 0 is 5. Product roll here. Derivative of that. And the second part of it, the derivative of that. Power, chain rule. Okay, let's plug this in. So x of t is 0. So x of 0 is 0. This one will go to 0. And for our second equation, so all the t's go to 0. This goes to 0. Minus 2 root 2 c1 plus c2. Those exponents go to 0. And we already have our c1 to 0. There we go. So our function, and this is our motion function. Find the time with the mass attains its extreme displacement. Extreme max min from equilibrium. So the derivative, we want to find, so we already found that function, but remember c1 is 0, so x prime of t, when c2 is 5, I can plug in 5. So it looks like I'll be able to factor that out. factor a 5 out too? While we're at it. This is never 0. Rationalize. So our extreme max, probably should plug it in. This is a max. This is our x prime of t. Sine chart looking here. I plugged in something bigger. This is negative, and this will be always positive. And there's the sine chart. So plug in this into our function. So there's our function. I just copied it. So our max occurs at square root of 2 over 4. Max is, which is approximately 0.65. Oh, what units are those? Feet, I believe.